All right, so yesterday we were simplifying radical expressions, and we learned 3 rules for simplifying radical expressions. One of them was to be in simplest form, you can't have any perfect square factors in the radicand. You can't have any fractions in the radicand. And the third one, which we're covering today, is you can't have radicals in the denominator of a fraction. So when we have radicals in the denominator of a fraction, we need to find some way to get rid of them. We're going to use a process called rationalizing the denominator. Now, the reason it's called that is because radical 7 is an irrational number. Okay, it can't be expressed as the fraction of 2 rational numbers. It's an irrational number. And so we want to turn it into a rational number. So that's a process called rationalizing. So what we're going to do is we're going to take our fraction and we're going to multiply it by something. But what is the only thing I can multiply my fraction by and not change its value? What is the only thing I can multiply a fraction by and not change its value? Yeah? 1. Okay? I can multiply it by 1. Okay, but we're going to use a special form of the 1. We're going to multiply by whatever radical is in the denominator over itself. So what's radical 7 divided by radical 7? 1. And so I can multiply by radical 7 over radical 7 and not change the value of my fraction, because I'm really only multiplying by 1. So I'm not changing its worth, I'm just changing its appearance. Does that make sense? It'll still be worth the same amount, but it'll look different. Okay? So when I multiply 5 by radical 7, there's really nothing I can do to change that. I just get 5 radical 7. But what's radical 7 times radical 7?
49.
Radical 49, which is 7. Which is a nice, rational number. That's as simple as it goes. I mean, sometimes you'll need to check and make sure that your fraction can't be reduced, but 5 over 7 doesn't reduce. You want to make sure the radical 7 can't be simplified, but it can't. Okay? But other than that, that's as simple as it goes. And if you're not sure if you got it right, then check it in your calculator. Do 5 divided by radical 7, and then do, in parentheses, 5 times radical 7 divided by 7. You should get the same value both times. Because, like I said, they're worth the same. Okay? These two are worth the same. They just look different. Okay? This one is simplest form because it follows all of the 3 rules that we gave yesterday. Make sense? Okay. So let's do another one. Radical 2 over radical 3b. What should I multiply by?
Radical 2.
3.
Nope.
Radical 3b over radical 3b.
Radical 3b over radical 3b. Since we're rationalizing the denominator, we got to multiply by whatever radical is in the denominator. Okay? So on top, when I follow my radical rules, what do I get when I multiply radical 2 times radical 3b? Isaiah?
Radical 6b.
Radical 6b. Okay, because we just multiply what's under the radicals. That's the step we learned in the previous lesson. All right, what do we get in the denominator? 3b. Okay, because whenever you multiply a radical by its twin, radical disappears. Okay. Yeah. So far, so good?
Mm-hmm.
All right, adding and subtracting radicals.
How do you get the 3b again?
Which 3b?
The on the bottom.
This one?
I got 9b.
No, if you multiply those 2 radicals together, you get 9b squared. The square root of 9b squared is the square root of 9 times the square root of b squared. What's the square root of 9?
3.
What's the square root of b squared?
B.
B. Okay. That's why when we multiply a radical by itself, the radical just cancels out. Okay? So adding and subtracting radicals, we got 4 radical 10 plus radical 13 minus 9 radical 10. So really, all we got to do is identify like terms. This is just like when we were adding variable expressions. Okay? You could treat the radical 10 like an x, the radical 13 like a y. Okay? Okay. So what do I get when I add 4 x's and negative 9 x's? Negative 5x. But x is just radical 10. Okay? It behaves the exact same way as if that radical 10 was a variable. Okay? I've got 4 radical 10s. I take away 9 radical 10s. Now I have negative 5 radical 10s. Can I combine the radical 13 with anything? No, because there's no like terms with the radical 13. It's just radical 13.
So we treat the 4 times radical 10 as if it's like one number as opposed to multiplying.
Exactly. This is all one number. Okay? We combine it just like we did if it was a variable expression. Now sometimes this is going to require that you simplify radicals first. Okay? The next example gives you 5 radical 3 plus radical 48. Now those don't look like the same radical, do they? No, but we can simplify radical 48. What perfect square goes into 48? 16 is the perfect square, and it goes in 3 times. So we can split that into radical 16 times radical 3. What's radical 16? Just 4. So we have 5 radical 3 plus 4 radical 3 for a total of 9 radical 3.
It's much simpler than
All right, why don't you try one of those? Let's try 2 radical 7 plus 3 radical 63. Give it a try, and then we'll look at it together. So, you start with 2 radical 7 plus 3 radical 63. We can split the radical 63 into radical 9 and radical 7. Right? Radical 9 equals 3. So we need to multiply that by the 3 that's out here. Okay, this 3. Okay? That has to get multiplied by the 3 here. That's what gives us 9 radical 7 down here. And so now we have 2 radical 7 plus 9 radical 7 for a total of 11 radical 7. All right?
That's the answer. It's up here.
Let's do one with multiplying.
like on their own, or
No, we'll do one together. First of all, if you see something like this, what would you think your first step would be?
distributive property.
Distributive property. So we're going to do 4 times radical 5. And then we do radical 5 times radical 20. What's radical 5 times radical 20? Radical 100. And radical 100 is 10.
That is super simple.
4 times radical 5 is just 4 radical 5. Radical 20 times radical 5 is radical 100. And the square root of 100 is just 10. Okay. Now let's do one where we have to FOIL. You guys remember the FOIL method?
Ew, foil's so disgusting.
What does FOIL stand for? First, outside, inside, last. So we got to multiply the first together. What do we get when we multiply radical 7 by radical 7? 7. Then we do the outside. Radical 7 times negative 3 radical 2. Take a second, make sure you got it right.
3 radical 14.
Negative 3 radical 14, because we multiply what's under the square roots, 7 and 2. Okay. What about the insides? Radical 2 times radical 7.
Radical 14.
Radical 14. It's like we're back in the 80s. It's totally radical. All right, and the last. Radical 2 times negative 3 radical 2. That's a tough one. Close.
Negative
3
3.
radical 4.
Wait, negative 3
3.
radical 4, which becomes 2.
Negative 3 radical 4, which becomes 2. Well, you're missing a couple of things.
Times negative.
You multiply negative 3.
Negative
and
6. Because the radical 4 becomes 2. You multiply it by the radical 3. You get 6.
Then you combine them.
So radical 2, we multiply it by the radical 2. All right, you just multiply what's under the radicals. You get square root of 4. Okay. Square root of 4 is 2. And so you multiply that 2 by the negative 3, which gives you negative 6. So now all we have to do is add our like terms. What do we get when we add the 7 and the negative 6? 1. How about negative 3 radical 14 plus radical 14? Negative 2 radical 14. So you got negative 3 of them plus 1 of them. Gives you negative 2 of them. Exactly. Everybody good? Yeah. All right. One more problem. It's a word problem. Everybody's favorite. The orbital period of a planet is the time that it takes the planet to travel around the sun. Okay, so what is the orbital period of the Earth?
365 days.
365 and 1/4 days. It's a year. That's how long it takes to travel around the sun. You can find the orbital period P in Earth years using the formula P equals radical D cubed, where D is the average distance in astronomical units of the planet from the sun. So since we're talking earth science here, does anybody know what an astronomical unit is?
I'd rather not.
Millibars. I don't know.
Millibars. That has to do with pressure.
Where is
Astronomical
it?
units has to do with distance. Yeah.
The distance between the planets.
No, the astronomical unit is a fixed distance, just like a kilometer. Okay? An astronomical unit is 93 million miles, the average distance from the Earth to the sun. That's what we use as a standard of measurement. Okay? You don't need to know that to solve this problem. I just thought it was a little extra to throw in there to make me sound really smart on YouTube. Okay? So D is the average distance of the planet from the sun. So first we want to simplify the formula. How do we simplify this formula?
P equals radical D squared times D.
That's right. We pulled the perfect square out of the D cubed. Okay? Because D cubed is D squared times D. Right?
Mm-hmm.
What do we get when we simplify that?
D radical.
D radical D, because the square root of D squared is D. Now, Jupiter's average distance from the sun is shown in the diagram. It's labeled as 5.2 astronomical units. In other words, the average distance from Jupiter to the sun is 5.2 times the average distance from the Earth to the sun. Okay, a little over 5 times as far away from the sun. So we want to use that to find its orbital period. In other words, the length of its year. So what do we do with that distance from the Earth to the sun? Yeah.
Plug it into the D, so 5.2 radical 5.2.
Plug it in for D, right?
Yeah, so then you times.
So then we plug that into our calculator.
You get 11.85.
Approximately 11.85 years. Earth years, should say. So every 11.85 Earth years, Jupiter completes one full trip around the sun, which means that in your lifetime, Jupiter has only completed one and some partial trip around the sun.
It's slow.
Yeah. So if you were living on Jupiter, you wouldn't even be 2 years old yet.
Yeah.
Okay. And you'd be super short. Well, some of you already are. Yeah, you're one to laugh. All right. Any questions? All right.